Thank you, Tom, and it's a pleasure to be here. I guess what I'm going to do in the first 10 minutes or so is kind of set the stage for this paper and this work. Um, my interest in pricing emissions goes back about 10 years. I was in the process of retiring from Goldman Sachs, and one of my partners there, Larry Linden, got me interested in this problem. And I remember early on, I said to him, Larry, it's obvious what needs to be done here. We have to price emissions. That's, as an economist, as a risk manager, that's pretty obvious. And Larry said, well, Bob, that is obvious. Everyone knows that. The problem is no one knows where to price it. And I thought, well, that doesn't sound right. And so I thought, let me look into this a little bit. And I started reading the literature. And it's not a very satisfying literature. And in some sense, this paper is an attempt to address some of the issues with that literature. And one of the big issues from my perspective as a risk management professional was that that literature didn't really spend a lot of time worrying about risk. It kind of, first of all, that literature started maybe 30 or more years ago. And the computer power that we had in those days wasn't really enough to do a very good job. And no one knew what the expected damages from climate change were going to be, much less the risk or the full distribution of potential damages. And so they didn't spend a lot of time on it. Now, when we think about, let me see if this is, okay, when we think about climate risk, there are a number of lessons that we can learn from financial risk management. So that was my background. I was head of risk management at Goldman Sachs. And so these are, I don't think any of these will be controversial, and they're sort of obvious points, but nonetheless, they're worth making. The first one is risk management requires consideration of worst case scenarios. Perhaps that should be obvious when you're named a risk manager in some position. That's exactly what you're supposed to worry about, worst case scenarios. And I only put this up because often when you have climate scientists talking about worst case scenarios, they're accused of alarmism. So I think you just have to frame it as, this is risk management 101. You have to think about what could happen. The full distribution of outcomes, and in particular, you don't worry about the good ones, you worry about the bad ones. Second point is the urgency of risk management, particularly a growing risk like climate risk. But basically, one way to think about this, and we'll come back and put this in context in our paper, but when you have enough time, you can solve almost any problem. So when you think about a risk management problem, the amount of time you have is a scarce resource. And that's why when you think about a risk, you think about the urgency of it. When you're in a financial institution and you say, we've got a risk, no one ever says, well, we're busy today, come back tomorrow or next week. Risk management is always a high priority. And in fact, when I was made head of risk management at Goldman, one of the issues that they thought about is, should that be a partner level position? And there was a lot of question about that, which, by the way, leads to the last point. Risk is what we measure, uncertainty is what we manage. This is kind of a common theme sometimes that economists talk about. It's often attributed to Frank Knight. So people sometimes talk about Knightian uncertainty as opposed to risk. Both risk and uncertainty refer to the full distribution of potential outcomes. But when this distinction is made between risk and uncertainty, the point that people are making is that you can measure risk. For instance, volatility is a measurement of risk, or value at risk is another measure of risk. There's all kinds of measures. And at Goldman Sachs, when they wanted to hire a risk manager, they knew that what they wanted was someone, a young quant like myself at the time, who could create a measurement of risk of various different types of positions that they might have on. And And yet they also knew that what partners of the firm did is they managed business uncertainty. They managed their business risks. And that wasn't just some number that came out of the model, because they knew that any model could be wrong, the world could change. There's all kinds of reasons why a measure of risk, like a value at risk, is just one input into the management of the uncertainty of a business. And so many of the partners at Goldman thought, well, you know, this young quant isn't really a partner level position. It's just giving us one input. It's not managing a business. And luckily for me, the other partners prevailed and said, no, risk management is important, and you have to have someone with enough stature in the firm to question the risk-taking of other partners at the firm. So they decided that head of risk management, which was the title they gave me, was a partner level position. And yet they realized uncertainty is a much more basic and broader issue than risk. And what we're going to talk about today is a measure of risk that we have come up with that applies to climate change. If you think about asking the question, how significant is the risk of climate change? One way to answer that is in terms of what is the appropriate incentive to reduce emissions. If it's a high number, it must be a serious problem. If it's a low number, it's not so serious. So that's basically the question we're addressing here. How serious is climate change? It's not an easy question to answer. And then finally, the third bullet point here, which I didn't mention, is that the purpose of risk management is not to minimize risk, it's to price risk appropriately. When the partners at Goldman Sachs said we need to have a partner named, you know, with the title risk management, they didn't say that because they wanted to minimize the risk of the firm. The firm was doing quite well at the time, taking risk and making money from taking risk. But what they wanted to do was to take appropriate risks, risks where we were getting paid appropriately for them, and not to take risks where we weren't getting paid. And so that's a different question than, or a different objective than minimizing risk. It's making the highest return for the risks that you take. And so as a risk manager, it's those trade-offs between risk and return that you're really focused on. And that's exactly the issue with respect to climate. It's that we're not pricing it appropriately, or at least Kent and I don't think we are. And we're trying to ask the question, what is the right amount to price climate risk? And not pricing it appropriately is a problem, because when you don't price risks appropriately, you don't take the appropriate amount of risk. If we're not pricing this risk high enough, then we're going to take too much of this risk, which is obviously what we're doing today. Now you might wonder, why do I have this rather dramatic picture of this flaming accident on Interstate 78? And the reason I like to put that up is, well, it illustrates kind of a worst case scenario, if you will. But it's also the case that I happened to be there when this happened. And so others might draw different lessons. But to me, this is a lesson about climate, because I was driving along here with my wife into the city. This is back December of 2014. And it was pouring rain when all of a sudden my wife exclaims, "Oh my God, Bob, watch out." And what she had seen was way in front of us on this side of the highway, way down here, this truck that was bouncing. It looked clearly like something was wrong. And when I looked up and saw it, I could see there was fire coming out of the passenger side wheel well. And so I thought immediately, you know, that truck, something's wrong. It's probably been in an accident. It looks like it's out of control. Now it's on the other side of the freeway, and I assumed it was going straight. It turns out it wasn't. There was also this concrete barrier between us that, I don't know if you can see it, it's about 2.5, 3 feet high. And I thought to myself, you know, that barrier is not that high. That truck, worst case, it could hit that barrier. There could be debris on our side of the highway. So get over to the right and slow down and be prepared for whatever might happen. Well, over the next 5 seconds, as we watched, that truck was not coming straight down the freeway. It had been in an accident way over here on what was the left side from our point of view. It had hit a truck, the truck had hit a car, the driver was killed immediately, and now the truck was sort of moving sideways, in fact, straight at a point right in front of us. And we watched as it hit that barrier, bounced up over that barrier, and landed right in front of us. And it wasn't just a truck, it was a tanker full of gasoline. So there was about 9,000 gallons, and it had a lit fuse. So when it landed in front of us, it burst into a ball of flame like that. Now, luckily, we were able to swerve and avoid hitting it, barely, you know, by like a fraction of a second. We were past it. The heat was incredible as we went by. The flames were right there next to the car. The car was covered in oil from this accident, but we missed it and we survived. We were, by the way, the only car that got past it. The traffic was stopped for the next 7 hours while they cleaned up this mess. So why do I say what does it mean about climate? Well, where we are with respect to climate today, I would say, is where I was when Mary exclaimed, "Oh my God, watch out." We have a risk that's coming at us, climate change. We don't know how bad it's going to be, and we have to prepare. And, you know, worst case scenario, it could be pretty bad. So what do you do when you have that kind of uncertainty, that kind of risk? Well, you react quickly. You don't wait. And what do you do? Well, in the case of climate, we have to price the emissions. We have to create appropriate incentives to reduce those emissions. So the price of emissions is the brake. And the question is, how hard do you slam on it? I don't think there's anyone who would say you shouldn't hit the brake immediately. And we can talk about what the cost of delay is, but it turns out it's huge. And what we're trying to answer is, what's the right price? Now, another way to think about this problem is the Earth's atmosphere is a reservoir. We're filling it up with a pollutant, greenhouse gases. And the problem is we don't know what the carrying capacity of the atmosphere is. This is a picture of the Johnstown flood. I don't know if you're familiar with this story. It's a true story. There was an old reservoir, and it was built to provide water for a canal. It was like the Pennsylvania equivalent of the Erie Canal. But it turned out they built a railroad, and the canal was never really used, so this reservoir was abandoned, wasn't needed. And then some rich industrialists from Pittsburgh decided, you know, that would make a nice hunting and fishing club. Let's fill it up again. And so they did. And they made a bunch of mistakes. But in May of 1889, there was a week-long rainstorm. It filled up that reservoir until it was overflowing. And this earthen dam, when the water overflowed, now one of the mistakes they made is they put a road across that dam so they could build houses on both sides, and they left the middle lower than the two ends. So the water started overflowing the middle, and as it overflowed, it caused erosion of the dam. That caused more water to flow, and it was positive reinforcement. And in a matter of hours, that entire reservoir drained down a narrow gorge and wiped out Johnstown, Pennsylvania. It killed over 2,200 people in a matter of hours. And so I think, do we have another picture? Oh yeah, this is downtown Johnstown after the flood. There's another picture of the main street after this flood. So that's my last slide. But the point is that if you think about the atmosphere as being a reservoir, we don't know what the safe level. You could think of the level of gases in the atmosphere as being measured in terms of parts per million of CO2. So at what point might you have a catastrophic event occur like the Johnstown flood? Is it at 650 parts per million or 450 or 550? You could think of that as being a probability distribution. The point at which you get the first catastrophic outcome from putting too much pollution into the atmosphere. And you could think of that point as being drawn from an unknown distribution. In other words, we might cross a tipping point at 450 parts per million at which a catastrophic outcome becomes inevitable. Maybe that doesn't occur till 500, maybe it occurs at 350. So you can think of that distribution as kind of a distribution that defines the risk that we're creating by filling up this reservoir. And we really have no idea what that distribution looks like. And that really leads to the uncertainty of climate change that we're trying to address. With that as an introduction, wow, I took too much time, but I'll turn it over to Kent. Here you go. I don't know if you want to.
Okay. All right, thanks for coming, everybody. I see a few people I know here. So what I want to do is talk about the model that we've developed and kind of explain the importance of this. But actually, before I do that, I thought I'd get started. I stole, a few of you may know, I'm doing a course over in the business school on the business of climate change with a guy named Jeff Heel and another professor, Patrick Bolton. And last week, we had in a scientist named Jason Smearden from the Lamont Earth Observatory, which is a Department of Columbia, and he's a really accomplished climate scientist. And I thought I'd give you a little bit of background as to what we know and what we don't know about climate change. So this is a chart that you can see here. You know, what is this doing in our talk? Because we've got names of different planets. Well, it turns out this is Venus, Earth, and Mars, which, as you know, Venus is a little closer to the sun than we are. Mars is a little further away. And what these show are roughly based on the amount of solar radiation that hits Venus, Earth, and Mars. What should their temperature be? Okay, now, as it turns out, let me jump and just talk about the Earth. One of the things that characterizes the Earth is pretty good at reflecting a lot of the solar radiation that hits it. This is called the Earth's albedo. Okay, so a large fraction of that is reflected. And it turns out if you take that into account, if the Earth had no atmosphere, the average global temperature of the Earth would be about minus 18 degrees centigrade. In other words, way too cold to sustain life. Okay? However, instead the Earth, the average temperature is about 15 degrees centigrade. So what's going on? What causes this? What's the physics behind it? Well, it turns out the Earth's temperature is driven by a very simple relationship. It's the equilibrium temperature. Okay, so what determines that? Well, it's driven by the fact that the amount of radiation that hits the Earth and gets absorbed also has to be emitted. Because obviously, if that weren't the case, then the Earth temperature would either go up or go down. Okay, so what's the way this happens? Well, for those of you who've done a lot of physics, okay, this will be pretty obvious, but I'll go through it anyway. Basically, the radiation that hits the Earth comes from the sun. The sun's very, very hot. Okay, so as a result of the sun being very hot, most of the radiation that we get from the sun occurs in the visible spectrum, the visible part of the spectrum. So what have we got here? We've got intensity of the radiation on the y-axis. On the x-axis, we've got the wavelength. So basically, it's short radiation, visible, some UV light that hits the Earth. Luckily, a lot of the, especially high-frequency UV light gets absorbed by the ozone, but you can see most of the visible light makes its way through the atmosphere and hits the Earth, and a large fraction of it gets absorbed. Okay, so that warms the Earth. Now, what determines how does the energy get released from the Earth? Well, this is governed by a phenomenon called black body radiation. So basically, as the Earth warms up, everything that warms up starts to glow. Okay, now the Earth isn't super warm, so it turns out most of the radiation that gets emitted by the Earth is in the form of infrared radiation. So you guys have all seen infrared images, right? Where you have people glowing and that kind of thing. Well, if you went out into space and took an infrared image of the Earth, even the dark side, you would see it's glowing just like people are in those infrared images. Okay, so this blue line here is what this spectrum would look like if we had no atmosphere. We do have an atmosphere, okay? The atmosphere, you can see, absorbs a lot of that infrared radiation. In other words, it acts like a blanket that surrounds the Earth. Okay, so why doesn't the Earth get really, really warm then? Oh, by the way, notice that most of the visible radiation makes its way down to the Earth through the atmosphere. But the trick is that even when the Earth gets warm and starts to glow with infrared radiation, only a little bit makes its way up, the infrared radiation makes its way up through the blanket of the atmosphere. There's just this little gap over a relatively narrow range of wavelengths where that infrared energy can escape. And what we know is that the amount of energy that comes in through the visible spectrum has got to equal the amount of infrared radiation that goes out. Otherwise, the temperature wouldn't be an equilibrium temperature, okay? Now, it turns out if you have some what are called greenhouse gases in the atmosphere, and there are very small amounts of these gases in the atmosphere, they'll start absorbing this infrared radiation, okay? There are a couple gases, water vapor absorbs a little bit of that, but it turns out the ones that we're most worried about are gases like methane and carbon dioxide, okay? And it turns out, particularly for carbon dioxide, you put a little bit of carbon dioxide into the atmosphere, okay? It starts to absorb this radiation. What happens as that comes down and down? Well, that means the Earth has got to get hotter and hotter to equilibrate, okay? So this is what we call global warming. This is climate change. So basically, as the amount of carbon dioxide goes up, the Earth acts as a better and better blanket. The visible radiation still gets through, so the Earth is going to warm up. Okay, so what's going on with carbon dioxide in the atmosphere? Well, this is a picture from Hawaii. Some of you, in fact, it's the big island of Hawaii, and right at the top, there's a big mountain, and there's an observatory up there. And it turns out since the late 1950s, they've been monitoring the level of carbon dioxide in the atmosphere. And this is a plot. The red line here shows the level of carbon dioxide since about 1958, 1959, okay? And you can see that over that time, the level of carbon dioxide has come up. This is from a couple of years ago. The level of carbon dioxide is now up around 410. Okay, it's going up by about 25 parts per million per decade. Now, the original concentration of CO2 in the atmosphere was about 280 parts per million. It's now up, you can see, quite a bit higher, not quite double where it was pre-industrial age, but pretty close. And at the same time, we're seeing a massive increase in the temperature of the Earth. Okay, you can see the Earth now relative to, again, the pre-industrial age is a bit more than 1 degree higher, which you might say, well, that's not that much, right? But there can be lots of changes associated with small changes in temperature. Okay, and remember, this is not the equilibrium temperature change. The Earth is continuing to go up because more and more energy is being absorbed by the atmosphere because of the increased CO2 concentration. And of course, the same amount of energy in the visible spectrum is hitting the Earth, okay? Now, what are the long-term consequences of this? Well, as Bob spelled out, we think there are long-term consequences. We don't know how bad they are, okay? One of the things that you probably heard a lot about, because there's been a lot of news on this, we're seeing some really severe evidence that suggests Greenland, the ice cap over Greenland and the ice cap over Antarctica are both starting to decline in a really dramatic way, okay? So to the extent the Greenland ice cap melts, that's going to result in about 7 meters of sea level rise, okay? depending on how much of the Antarctic ice sheet melts, that could lead to sea level rises, which could be far, actually this says 4 to 6 meters, but that's if a relatively small fraction of it melts. Turns out if a lot of it melts, it could be far worse, okay? What could this do? Well, this is, when you first process this, at least for me, it was a little hard to see, but this shows what 20 to 30 meters of sea level rise would do to New York. Okay, if you look closely here, you can see this is Manhattan, okay? This is, in fact, this is where our new business school at 125th is going to be. It's underwater, which is a little disturbing for those of us in the business school. One of the things that we as humans have done is we've built a large fraction of our infrastructure right on the coast. Okay, and that's a little disturbing because that means a large fraction of that infrastructure could be destroyed. It turns out there's some real severe problems with other things, with crops, with lots and lots of things. Now, how certain are we that all of this is going to happen? Well, we're not, okay? We know there are going to be damages associated with both sea level rise, associated with even the ability of people to live, to survive without air conditioning or some form of artificial sustenance in places like India, in places like Arizona. We know Bangladesh, for example, would be completely underwater with this sort of sea level rise. Okay, and what are the geopolitical consequences of that? There are huge damages, but the standard deviation around these things is even bigger than the magnitude. So how do we go in and assess this? Well, the argument that we're making, okay, so let me jump now to talking about our paper. What's going wrong? What's going wrong is that each of us pump out CO2 through our daily activities, okay? And we're arguing there are negative externalities associated with this. In other words, if we all jointly pump a lot of CO2 into the atmosphere, the Earth's blanket becomes even better, the Earth warms up, okay? How can we avoid people doing that? Well, the standard argument that you get from an economist is that if these sorts of activities lead to potential damages, you've got to price those activities. You've got to put a price on pumping more carbon into the atmosphere. How do you come up with that price? Well, the way you've got to do it is you've got to estimate what the damages are associated with each additional ton of CO2 that gets pumped into the atmosphere, and then you've got to price that, okay? So what we're trying to do is we're trying to lay out a model, okay, that tries to come up with the damages associated with 1 additional ton of carbon dioxide being pumped into the atmosphere. So what I thought I'd do, I'm not going to take very long here because I want to give Bob a few minutes to talk about one additional thing, but just very quickly run you through the logic of this model, okay, and a couple kind of key features of the model. So what's the idea in our model? And by the way, let me emphasize again, for those of you who've taken, for example, Emmanuel's classes, you know models are a bad thing. They're often things that you leave out of a model, and we want to emphasize that that is very much true here. There's probably a ton of stuff going on that we're not capturing, which we would argue is all the more reason to be cautious, okay? And what does being cautious mean? Well, it probably means putting a higher price on carbon emissions, trying to slow carbon emissions even more quickly, okay? Okay, so what are we trying to capture? We're trying to capture the link between greenhouse gas emissions, like carbon dioxide emission, and consumption damages. Okay, so what's the stream of causality? Well, we're arguing that greenhouse gas emissions every year lead to higher greenhouse gas levels. That's something that we know for sure. There's no uncertainty here, right? This is something that for sure is going on. We know greenhouse gas levels lead to higher temperature change. We're relatively certain about this relationship. There's still some uncertainty in this though. And where there's a lot more uncertainty is when the temperature goes up as a result of these increased greenhouse gas levels, what's that going to do in terms of damaging people? In other words, driving down what we're going to label, because we're economists, as consumption. But remember, consumption includes everything. It includes well-being. It includes how much food you eat. It includes your standard of life. It includes amenities, like the fact that, you know, lots of places that we used to love are destroyed. There are lots of places in the earth that are not habitable, okay? All right, so how can we fix this as humans? Well, the avenue that we're going to explore is mitigation. What does mitigation mean? It's just a fancy word for how do we get people to put out fewer greenhouse gas emissions. And the argument we're going to make is you got to price them. You got to charge people for pumping these things out, because pumping these things out is potentially doing a lot of damage to the rest of society, okay? Now, the way we're going to solve our model is we're going to do this in what's called a representative agent framework. So the basic idea here is we're going to assume that we as a society can all get together, okay, and kind of act as one individual. In other words, take into account the amount of damage we're doing by pumping greenhouse gases into the atmosphere and set the level appropriately. Okay, we're going to do that, and then we're going to back up and say, okay, what level of taxes would cause that level of emissions to, that level of mitigation, that cutback in greenhouse gas emissions to actually be implemented, okay? So now the key thing there is, well, how do we figure out the damages? The problem is that there's a lot of uncertainty. Okay, so I'm going to go through how we characterize this uncertainty, but be aware this is a pretty big distribution in terms of, you know, for a reduction of 1 ton in CO2 emissions, how much is this going to affect human consumption from now over the next several millennia? Because that's really what we're thinking about. Okay. Now it turns out one of the key factors in our model, okay, is risk. Because again, there's a lot of uncertainty about this, and as Bob emphasized, what you really have to worry about here is the tails. You have to worry really about the really bad outcomes, okay? Now, from an economic perspective, what this means is if we get one of these tail events, so if the Earth turns out to be much more fragile than we had anticipated, what that means is that people are going to be really bad off, and they're going to really say, boy, we wish we had mitigated more in the past, okay? A fancy way of saying this is that the marginal utility of consumption is higher in these really bad states, okay? So how does this risk get incorporated into our model? Well, it turns out I think one of the first papers to really try and integrate into a climate model like this, the pricing of financial assets. Okay, so basically the way we're going to calibrate the risk aversion, in fact, the very nature of risk in our model, is by looking at stock and bond prices. Okay, so what do I mean by this? Well, this is a plot going from 1871 up until 2011. And here what we show is, with a log scale, we show if you'd invested in the stock market, how well would you have done? And if you'd invested in bonds, how well would you have done? Okay? So you can see stocks do a lot better. In fact, over this very, very long period, the stock market has beaten the bond market by almost 5% a year. How come? Well, the standard answer we give is because stocks are risky. Okay, now what does it mean that stocks are risky? Is it volatility? Actually, anybody know? Any of my students know? I hope so. Okay. Well, it's not volatility. How do we know this? Well, let me show you the return on another portfolio, okay? Another portfolio that you can build is, instead of buying stocks, what you can do is you can go short stocks, right? You could invest some money in bonds and then short the stock market. How well would that portfolio have done over time? Well, that's this green line right here, okay? So you can see that green line right here goes down by about 310 basis points a year. It's equally volatile. If it's equally volatile, why does it go down so fast? Well, the answer is because this is like insurance. Okay, the stock market is anti-insurance, right? What makes the stock market risky? The stock market does really, really well when the global economy is doing well, right? When you've got a job, okay? The reason people don't like to buy stocks, we think, is because stocks go down when you really, really don't want them to go down. When you lose your job, right? When the economy is doing crappy, that's when the stock market falls. So it's kind of like anti-insurance. Shorting the stock market provides a form of insurance, okay? So what we want to incorporate into this model is when is climate damages going to hurt you most? Well, climate damages are more like insurance, right? They're more like kind of shorting the stock market. So it turns out, this gets a little technical, but basically what we want to do is those damages way out there, you want to discount them at a very, very low rate because they're like insurance, okay? Turns out what this does is drives up the price, the present value of those future damages, okay? So it really emphasizes, we think, the urgency for pricing CO2 emissions at a much higher level, in fact, mitigating much, much more than we are currently doing. I'm going to skip over a whole bunch of this. In fact, let me, okay, so what happens when you mitigate? Well, basically you pay a cost today because it costs you to mitigate, right? Using the capacity of the atmosphere for free, from an individual perspective, that's great, right? Because you don't have to pay these costs to build new technologies like solar, whatever, okay? So you pay a cost, but of course, in the future, if you mitigate today, if you have higher mitigation, you're much likely to have lower damages in the future. So it's always a trade-off between consumption today and consumption in the future. And what we're arguing with our model is that the trade-off is you should be incurring that cost today so as to avoid damages in the future, okay? Again, I'm going to skip through a lot of this just because I'm really running short on time. There have been some estimates. There's one very famous study by McKinsey that looks at the cost associated with the new technologies. You can see they've looked at kind of the whole menu of things that you can do to bring down carbon emissions, solar technology, you know, all the way up to retrofits of plants, all the way to extracting carbon from the atmosphere. So we build this all into our cost models. Where do we get the damage models? Well, the damage models, let me mention too, in terms of the cost, one of the things that, in case you're worried, we're building into our model is we know that as we move into the future, the cost of mitigating CO2 emissions is going to become cheaper, okay? So why not just wait until it's really, really cheap in the future? Well, the problem is that, kind of as Bob emphasized, the problem is the amount of CO2 in the atmosphere, if we keep emitting like we're doing today, it gets higher and higher and higher, and we may reach a point where there's no turning back, where basically we've damaged things so severely that, and the cost then of extracting carbon from the atmosphere so as to cool the globe down becomes crazy. But anyway, we have built technological change into the atmosphere. I'm going to skip over that. Okay, damages. I showed you sea level rise. Again, there are lots of damages. There's a huge amount of uncertainty. The way we calibrate our basic damage model is we look at all of the different climate models that are out there, and we look at the differences in the outcomes you get from these models. It turns out there's a huge variance in the outcomes of these models. Okay, and one of the reasons we think we might very well be underestimating the amount of uncertainty is because, you know, there could be some common flaw in these models that we're not aware of. So I'll tell you, how do we deal with this? Well, we have two parts of our model. One, the part I just talked about, is what we're going to call non-catastrophic damages. So think of this as the uncertainty that comes from looking at the different models and saying, what kind of differences do we see in outcomes, okay? The other part that we're going to build in is something I'm going to call catastrophic damages. Okay, and this is something that's gotten a lot more attention in the climate literature recently. And it's this idea that, let me jump to the catastrophic damages, is that if we get to a certain temperature, certain temperature increases, all kinds of really bad stuff can happen. So for example, if there's a big enough temperature rise, the Arctic tundra can melt. This can release lots of additional greenhouse gases. You can get a positive feedback effect, which could lead to massive increases of CO2 in the atmosphere and massive temperature increases. And it could, very, very bad outcomes. So these things get called tipping points. So what's the probability we hit a tipping point and how bad are the damages? Well, so we build a set of models where basically this is the probability of hitting a tipping point as a function of the temperature rise, okay, from current levels of temperature. So it turns out the model that we're gonna adopt, okay, which is based on some evidence out of the literature, but really we're just making a guess here because the scientific literature is not very far along on this. We're going to use a tipping point of 6 degrees. So that means if we get up to 6 degrees above current levels of temperature, which is a massive rise, okay, we hit a tipping point for sure. How bad are the damages associated with the tipping point? Well, again, we're going to be relatively conservative here. We're going to use a curve that says there's almost zero probability of really, really severe damages to economic output, but there's still some probability of a fairly substantial hit to economic output, okay? This plot just shows that we're being relatively conservative. If we go to more aggressive disaster parameters, you can see we're going to get a much, much higher cost of CO2 than what we built into our model. Okay, let me just show you some of the last thing, finally. We've solved this all in a, we're going to assume a time series process. And again, what's changing as you move through, okay, so here you're moving through time in the x direction. In the y direction, you can see there's a tree here, structure here. And you can think of this just like a standard option pricing tree, okay, or something where you're having some evolution of some parameter over time. What's evolving here is our knowledge of how fragile the atmosphere is. Right now, we don't know. We don't know if it's going to be really, really bad or not so bad at all, okay? And basically over time, you're learning how bad, how fragile is the atmosphere, okay? Let me show you some numbers, okay? So this is, I hope these are probably not legible at all, but let me give you some of these numbers. What this shows in our tree, how does the price associated with carbon emissions evolve, okay? So the current number that our model comes up with is $126.51 per ton, okay? Bob, what does that correspond to in like tax on a gallon of gas? About $1.25. Okay, so fairly substantial, but not huge, okay? Now you can see as you move down in the tree, this number goes way, way down. Down here it's $3.74, here it's $10.94. Why is it going down? Well, because if you move down in the tree, what you're figuring out is that the Earth is actually really rather robust. It's not as much of a problem as we thought. The damages aren't going to be that bad. But if you go up in the tree, you can see those numbers get a lot bigger for a while, reflecting the fact that here, that's really bad news. That's finding out that, yeah, we need to be really, really careful. We need to be doing a lot of mitigating. Okay, again, where do these numbers come from? Well, these are the carbon taxes that are required to implement a certain level of mitigation. Okay, so this chart shows the amount of mitigation of CO2 that we're doing. You can see with that putting in a tax of $126 today would give you about 70% mitigation of all CO2 within, a certain amount, within the amount of time required to implement all of these various measures. You can also see, this is really important, that by the time you get out 100 years or so, we're up to a level of above 100% of mitigation. What does that mean? We're using technology to actually pull carbon out of the atmosphere and store it underground, okay? All right, why don't I skip over all of this? There's obviously a lot of stuff here. One last thing that I want to emphasize before Bob says a little bit about what we've seen more recently is just one of the nice things about a model like this is it allows you to think about different aspects of this problem in hopefully a new and innovative way. One of the things that I think is most important is costs of delay, okay? So as you guys are well aware, with the current political environment, we're not really doing very much about this problem, at least in the US. And what are the effects of this? Well, again, you can think of the atmosphere. We're filling it up with CO2. It's really very much the case that people are not only not being charged to put CO2 into the atmosphere, but in fact, in lots of countries, we have subsidies for heating oil, that kind of thing. So in other words, people are being paid to put more CO2 into the atmosphere. It's criminal. Okay, so what are the costs associated with this? Well, one of the things we do is we ask, what's the cost of a delay associated with implementing proper levels of carbon taxation, okay? And it turns out if we are to delay about 15 years, the costs associated with this in terms of annualized consumption are really, really high, about 36% of consumption. And if you work that out into current dollars, it's about $180 trillion, okay? So the costs we're forcing future generations to pay by not implementing carbon taxation immediately are really, really high. Now, again, all these numbers are estimates, right? But the one thing you don't want to do is say, well, it's uncertain, we should do nothing. You know, as Bob emphasized right at the beginning, that's the worst possible response to seeing a risk on the horizon. Okay, with that, let me turn it over to Bob.
Okay, well, this is the graph that shows, oh, yep, thanks. You know, people often ask, what does this mean for investors? I talk to investors a lot, and I say, well, if we price emissions, and rather than divest, which it turned out wasn't quite expensive for us, we only had about 1% of our portfolio invested in stranded assets, but it was scattered throughout the portfolio. It was in private equity, hedge funds, public equities, and we would have had to turn over something like a third of our portfolio. It would have cost a lot of money. So what we decided, rather than change the portfolio, we added an overlay to hedge that risk. We called it a stranded asset total return swap. It was a very simple derivative structure where we received the total return on the S&P 500, and we paid to a third party the total return on a basket of stranded assets, coal, tar sands, and oil exploration and production companies. Now, what's happened over these last 4 years? It's been a very good story. The stranded assets have underperformed the market portfolio by over 13% per year. And it's kind of an interesting time series here. This started in January 2014, kind of bounced around, not doing much for about half a year. And I'd like to point out that in May of that year, Stanford University was the first university to announce divestment of coal. And that was at kind of the worst time in this history. Since then, it's gone up a lot, basically peaking right after the Paris Agreement in, I guess it was December of 2016, 15, I think it was, yeah. And since then, it's come down a little bit, although you can see actually Donald Trump was elected right about here. It did poorly for about 2 weeks, and then since then, it's actually done fairly well. Although right here, when the Republicans passed tax reform, that was very good for the fossil fuel industry. So this swap did not do so well when the tax reform act was passed. But anyway, I think the main message that I wanted to get across from this graph is that in case you're feeling like we're not addressing this problem, markets are forward-looking, and I would say they're actually building in relatively strong expectations that we are going to price emissions sometime soon, at least in terms of the underperformance of these fossil fuel companies relative to the market. Now, do we have time for some questions? Yeah, okay. Lots of time.
Lots of time for lots of questions.
Okay. Why don't we take questions? Any questions? Yeah.
Yeah, thanks very much for a nice presentation. The fact that solar and wind are now, new installations are now at about half the cost of fossil, cheapest fossil, and batteries are about headed to that price point. How does that change your thinking on what the price of, I mean, the disaster price at this time will not change, but in terms of the fact that the rate of mitigation would kick in very much more rapidly than what you may have assumed, does that change your view?
Well, it does affect the valuation in theory. And
Right.
so you might say in a model, I can't emphasize, there's a lot of reality that we haven't built in. We have not built in, other than to say we've built in a technology that improves over time, and so therefore lowers the cost over time of reducing emissions. And so you might say we could capture that by increasing the rate of technological improvement. And that's one of the parameters we play with. And it's actually kind of interesting because it's not, it doesn't have a uniform impact. The initial impact as technology goes up is that, correct me if I'm wrong, you do less.
Well, I think it depends on its exogenous or endogenous.
Yeah, there's both exogenous and endogenous technological change. The endogenous is the more we do, the more we learn, and the faster that price goes down. So that's part of it, I guess. Yeah.
So that actually results in an increase in the price.
Right. So that increases the price of emissions at first, and then it comes down more quickly because you're getting faster technology.
And you also have a smaller stock in that. Right? So you push everything point out further.
Well, you make the probability of the tipping point being reached lower.
Yeah,
Yeah.
that's what I mean.
Yeah.
The other thing is that, you know, we have about a decade where oil prices were actually more than $1.40 higher than what is where they are today. Did we actually see much of a drop in consumption? Because my guess is energy use will keep increasing. So just putting a tax really will not do it.
Well, you know, there's a short run response and a long run
Sure.
response. And so the short run response is that people spend more on gasoline because they have the same automobiles. But over the long run, if the price of gasoline goes up, people buy more fuel efficient cars, they drive less. And so over, you know, a 10 or 20 year period, pricing of emissions is expected to have a big impact on the kind of vehicles that people drive. May lead to electric vehicles more quickly, et cetera, et cetera. So I would say it's very true that we don't know precisely what the impact on emissions will be of a given price. That's uncertain. We can learn a lot about that by pricing emissions, watching what happens. As an economist, I tend to be pretty optimistic that prices like $1 a gallon will actually have a very significant impact on the amount of fuel use 10, 20 years out. And what is true is that the rapid drop, let's say, in the price of solar, for instance, has led to a more rapid drop in emissions than obviously would happen otherwise. And that's a good thing in the context of this model. But we still have a strong presumption that, you know, pricing emissions is the solution, and we just don't know what the price will be necessary. But we can certainly learn a lot about that over time by pricing emissions reacting to it. One of the things that's part of our model, and we didn't perhaps emphasize it, is that you're learning through time as you move through that tree. That's you're actually learning about the in our model the fragility of the earth, but more generally we're going to learn about technologies and, you know, what it's going to cost and so on. And so we should react to that new information, and that's part of what distinguishes our model from a lot of the other models that don't take learning into account. Kent, do you want to add anything?
Yeah, I'd just say, you know, again, if you look globally and kind of integrate over all the different regions, what you see is globally there's a negative tax growth. You know, their subsidies are larger than the taxes, and clearly we've got to reverse that. You know, the correct price, our model is arguing for something more aggressive, but basically by taking a stand that there's a relatively small probability of a fairly bad disaster. But I think scientists are more and more convinced. You know, we've seen lots of We see good news on the cost front in terms of the cost of solar and wind and, you know, lower costs of storage, but we've seen really bad news in terms of the damages. We've seen, it's a little disturbing for Bob and I because we live in New Jersey, but not within the last couple of years, there was a big chunk of the Antarctic ice shelf that broke off. It was about the size of New Jersey. So for those of you who live in New Jersey, I guess that's a bad thing. Anyway, there are, we're seeing much, in particular for the sea level rise, we're seeing much worse news than most scientists had anticipated.
And one other thing, I mean, there's a lot of things that we didn't take into account in this model. One is solar radiative management.
Yeah.
So as Kent mentioned, one of the things that's really critical here is the equilibrium between heat coming in and heat going out. And it turns out it's actually fairly cheap to send particles up into the stratosphere that will increase the radiation leaving the Earth. And so therefore bring us back into balance at cooler levels. Now, there's risks associated with that. A lot of people don't want to think about that. And we didn't model that. But what is true is you have to think about that as reducing ultimately the risk, and therefore that would lower the price. We didn't model that. There's a lot of other things we didn't model as well. Other questions? There's a question.
Is there any technology that can remove carbon from the air? And if so, is it very costly or?
There are technologies for removing carbon from the air. For instance, you can plant trees, let them grow, bury the trees. That's a simple technology. In fact, it's probably the cheapest. But there's many other technologies as well. It's really just a question of cost. And so in our model, we build what we call a backstop technology, and we set that. Now, in our model, we're saying there's a technology at scale that can remove as much carbon dioxide as you want at this price. And we can set that at $300 a ton or $2,000 a ton. What I'm told is that at scale today, it would probably cost between $500 and $1,000 a ton. You will see people who will make claims that they can remove carbon dioxide much more cheaply, but they're often doing things like using residual heat that they assume is freely available from some industrial process or something, which may be true on a small scale, but would not be true at the scale required to, take carbon dioxide. So carbon dioxide removal is something that a lot of people are thinking about. A lot of research is being done, but the bottom line today is it's a very expensive technology. Although it's a very important one in the sense that even in our model, if you think about it, if there's a technology for removing CO2 that costs, let's say, $100 a ton 30 years from now, 50 years from now, then you can back into how much is the most you should ever pay today not to put that carbon dioxide in. In other words, it puts a ceiling. You wouldn't spend $300, you wouldn't even spend, let's say, $90 today not to put CO2 into the atmosphere if you can remove it for $100 down the road.
A little bit down.
A little bit down the road.
Yeah. And by the way, we built into our model, there's some technology in the future that's going to be developed that's not super expensive. You may have noticed that in the tree, we've got mitigation above 100%, and that's basically what that is.
Yeah.
So
Most scientists do assume we're going to be pulling carbon dioxide out of the atmosphere. So that is the margin that you should think about. The carbon dioxide that we put in the atmosphere today, we're probably going to be pulling out. And it's probably going to be relatively expensive at some time in the future. But you wouldn't pay more than that not to put it in today. It kind of puts an upper bound on it.
What do you have to do besides adding a tax on gasoline? I mean, what are the other implementable things besides the carbon?
Oh, well, we don't go into this, but a carbon tax would typically be done on coal, and on oil, and on natural gas. And then there might be other things that are done in other, like concrete releases. When you make concrete, it releases a lot of CO2. So you might have to do that. When you get into the details, I mean, of course, it gets rather complicated. But in terms of taxes, the carbon tax is actually pretty straightforward. There's only about support something called the Climate Leadership Council, which is the initiative started by Jim Baker and George Schultz, and that's actually developing a carbon tax that could be legislated. And so, you know, we're down in the weeds as to how that would be done, but it's not really that complicated in terms of taxing.
Well, actually, if I could add one thing to that, the one place that a carbon tax has been implemented relatively successfully is actually British Columbia in Canada. And it's a low level compared to what we think would be optimal. But it's been successful there. They were very clever. In fact, this is the nature of our carbon tax. It's consistent with that. We're assuming that the tax is fully rebated back to, so it's a revenue neutral tax. And this is what they've done in British Columbia. And it turns out when it was initially implemented, there were, you know, if you looked at opinion polls, it wasn't super popular. But what they've done is people receive a check every year, which is their pro rata share of the carbon tax. This, by the way, will not make it any less effective if you think about the economics behind it, right? People love receiving these checks. So it turns out now this is an incredibly popular tax. So you need to be clever, I think, from a behavioral perspective about the way that you implement this. But it's, you know, doing it right, it looks like this could be successful.
Yeah, no, that's right. And that the Climate Leadership Council proposal also is a revenue neutral rebate, and it would be about $500 per person per year in the U.S. So family of four would be $2,000. And if that's done, 70% of the population would be better off, primarily less wealthy individuals who don't do as much travel. So you know, your carbon footprint is probably biggest if you fly a lot. So, you know, and there are different places you can calculate your carbon footprint, but most people would be better off. So it's a progressive tax actually, if done that way. Now, a lot of people will tell you it's unlikely to be done that way because you have to get votes in Congress. Getting votes means you want to give congressmen things to spend money on that they want to spend money on. But that's a political issue. Yeah.
I have a question from the investor perspective. So do we have some ways to track how sensitive a stock or a particular fund like related to the climate change or something like that?
Right now, there's not a lot of disclosure, but as you may be aware, there's a lot of initiatives to require more disclosure. So, for instance, there's something called green bonds that anyone can issue. They can put a name on it. It doesn't really need much. Different green bonds that are issued by different corporations or government entities around the world do very different things. And so they're just starting now to develop standards for green bonds. On the corporate side, you may be familiar with something called the Task Force for Climate-Related Financial Disclosure, or sometimes called the Bloomberg Task Force. It's a proposal that was sponsored by originally the Group of 20, which asked the Financial Stability Board to figure out what should be done in terms of disclosure. Financial Stability Board appointed this Bloomberg Task Force, and they've now come up with proposed disclosure for corporations to give about climate-related issues. And so that's being implemented. It's in early stages. There are other initiatives, something called SASB, which is the Sustainable Accounting Standards Board, has proposed disclosure. So there's a lot of disclosures coming. And there's a lot of shareholder resolutions that are being sponsored and voted on. Last year, 3 big fossil fuel companies had votes against management on climate-related shareholder resolutions, including Exxon and Occidental Petroleum. And so there's a lot of work in that area.
Bob worked on pushing these forward, by the way.
One of the things I do in my spare time.
I was interested in the British Columbia experiment we talked about. So what happens to the money that corporations pay as part of corporate tax? Is that also related? Because I mean, corporations would be far more efficient. They would just price that and they would continue to impose it to the
Corporations will pay the tax and then they'll add that cost to the cost of the fuel or whatever you buy. So the cost is passed on.
I mean, a lot of corporations use energy, right? So they would, if you're talking about rebating the money back to the corporation, they would just be far. I mean, the behavioral shift would work on them because they would just be far more efficient. They would realize that the net balance sheet, they're seeing the money go back to them.
Well, the money that you pay depends on how much pollution you create, whereas the money you get back is done on a per capita basis. I believe in British Columbia, it goes back to individuals, not corporations.
That's right.
But even if you gave it to corporations, as long as it was per capita or, you know, based on something other than the amount of pollution,
But-
you would still have the right incentive.
Right. Hopefully, every corporation is providing some good or service in the end, right? Or some intermediate good that eventually flows into consumption for individuals, right? That's kind of the idea. So if you rebate individuals, right, then you're going to penalize them in the sense that they'll pay higher fuel costs, they'll pay higher costs for goods that are very carbon intensive, but then they'll get this rebated back. So this will incentivize them to buy less of the goods that are very carbon intensive, to use fewer, you know, lower levels of fossil fuel. Okay, but in the end, it's revenue neutral.
Oh, and so the rebate is not a function of how much carbon, carbon in any product because it's a fixed amount.
No. The rebate is absolutely it is equal to the amount of taxes that are collected every year.
But for the individual,
For the individual, yeah, definitely not.
Oh,
Right? So it doesn't matter. The rebate you get is a fraction of the total taxes collected. It has nothing to do with how much carbon you use. So the penalty you pay, right, effectively is based on how much carbon you use, how much carbon your activities emit.
and the amount of money you receive is a function of what everyone does.
Yep.
So it creates the right incentives. And the beauty of it is no one has to know this is going on, right? This is all built into the prices of goods and services. So you don't have to think about, should I eat steak today or should I eat chicken? Well, steak has more carbon content, or
It's priced in.
it's just all priced in. So you don't even have to know why you're doing the right thing, but you do the right thing when it's priced. And when it's not priced, everyone makes the wrong decisions because you have no way of keeping track of all that information. Pricing is really very information efficient. People don't often understand that.
I think perhaps we should stop there and thank the speakers for a very interesting